So hello everyone again. This is the final lecture of ray optics and optical instruments, that is lecture 5 part 2. So let's start the discussion directly. So I am Sameer Lavankar. Let's begin our final discussion. Okay, so right now we are on the optical instruments part, and right now after the completion of microscope we are discussing telescope right now. So let's move directly telescope only. So in the previous lecture we understood first of all the things which you need to remember. First is the angular magnification of a telescope is equal to beta by alpha, which is equal to f naught upon fe. The next thing is that you should need to remember what is the length of telescope tube. Length of telescope tube is f naught by f naught plus fe. Then next thing is, so basically if a lens in the place of lens, in the place of objective lens, if a mirror is being used, then that division of telescope or that part of telescope or that those telescopes are called as reflecting telescopes. Then this was one of the example, that is Mount Palomar telescope, that is in California, which is very high, which has a very large diameter, which is 200-inch diameter. Okay, let's move to the discussion now. So one such arrangement using a convex secondary mirror. So in the place, so basically if you are using a convex secondary mirror here to focus the incident light which now passes through a hole in the objective primary mirror. This is known as Cassegrain telescope after its inventor. So basically these types of mirrors are called as Cassegrain mirrors or Cassegrain telescopes. So one such arrangement using a convex secondary mirror to focus the incident light which now passes through a hole in the objective primary mirror, as you can see, which now passes through. So this is the basically hole, and it passes through it. So these type of telescopes are also known as Cassegrain telescopes after its inventor. It has the advantages of a large focal length in a short telescope, quite evident. So basically you will get what is the major aim. If the focal length is very much high, f naught is very much high, then the magnification will be very much higher. So basically what aim is to get a higher focal length. If you are getting a higher focal length, then our thing is completed here. So it also has the advantages of a large focal length in a short telescope. The largest telescope in India is in Kavalur, Tamil Nadu. So this is the telescope being formed here. So this is that largest telescope which is available in India. So the largest telescope in India is Kavalur, Tamil Nadu. It is a 2.34 diameter reflecting telescope, Cassegrain. So what does reflecting mean? Reflecting means if a secondary objective is not a lens, it is a mirror, then it is called a reflecting telescope. And what is Cassegrain? Cassegrain is basically an arrangement of a telescope in such a way that the convex secondary mirror is used to focus the incident light, which now passes through the eyepiece, through the hole and that to the eyepiece, objective primary mirror. Fine. So it was a ground polished setup and is being used by the Indian Institute of Astrophysics, Bangalore. So basically Bangalore uses it, Indian Institute of Bangalore uses it right now, even today also this is in use. The largest reflecting telescope, again the largest reflecting telescope in the world are a pair of Keck telescopes. So these are a pair of Keck telescopes, as you can see, this is the image, in Hawaii, USA, with a reflector of 10 meters in diameter. So as you can see, in India only 2.34 diameter is available, but in USA 10 meters diameter telescopes are being available. Okay, so that were some of the examples of telescope. Angular magnification is also been explained, and hence that is the complete end of your ray optics and optical instruments. So our ray optics is being explained. After this lecture you may have heard of wave optics also. Wave optics basically considers wave theory to consider of light. So you can even visit those lectures also. So ray optics consider discrete particle theory of light, wave optics consider your wave particle theory of light. Basically the electromagnetic spectrum is being explained there. Different concepts which cannot be explained by particle theory are being explained in wave optics concept, such as diffraction, polarization, scattering, etc. Why does it happen? Why don't we take it into culture? Why does discrete particle theory cannot explain those phenomena? What is Huygens principle, etc. will be dealt in wave optics concept. So that is different lecture series. You can even view that. For right now, let me just summarize the complete concept we understood, and let me close this complete lecture on ray optics and optical instruments. So let's move on to the summary now. Okay. So the reflection is governed by the equation angle I is equal to angle r, and the refraction by the Snell's law, that is sin I by sin r is equal to n, where incident ray, reflected ray, refracted ray and normal lie in the same plane. Quite evident, the complete mixture of angular laws of reflection and the law of refraction. Angle of incidence, reflection and refraction are I, r dash and r. So this is angle of reflection and this is angle of refraction. Fine. What is n here? N is nothing but the refractive index of medium 2 with respect to medium 1. Okay. So this thing has been done. Next is the critical angle. So, basically a concept or summarization of your total internal reflection. So, the critical angle of incidence IC for a ray incident from a denser to a rarer medium. Please make sure total internal reflection only and only occurs when the ray of light is moving from a denser medium to a rarer medium. Why? Because always when a light move from a denser medium to a rarer medium, the ray of light bends away from the normal. If you do it reverse, then the ray of light will bend towards the normal, and then there is no chance that the total internal reflection will occur. So, total internal reflection only and only occurs when the ray of light passes from a denser medium to a rarer medium. Okay. So, the critical angle of incidence IC for a ray incident from a denser medium to a rarer medium is that angle for which the angle of refraction is 90 degrees. For I greater than IC, total internal reflection occurs. Multiple internal reflections in the diamond IC is approximately 24.4 degrees. Totally reflecting prisms and mirage are some examples of total internal reflection. Optical fibers consist of glass fibers. So, basically this thing is just explanation of total internal reflection, and now this is one of the application, or this is one of the examples of your total internal reflection. What is optical fibers? So, optical fibers consist of glass fibers coated with a thin layer of material of lower refractive index. Light incident at an angle at one end comes out at the other after multiple internal reflections, even if the fiber is bent. So, even if the fiber is bent, even if it is like this also, then also the total internal reflection happens. These are formed in such a case that total internal reflection happens. Okay, fine. So, as one of the basic example, one of the basic reasons for optical fibers more successful applicability is because of its angle of incidence or critical angle being very less. Okay. Next is Cartesian sign convention. So, the major portion of this complete discussion of ray optics is you just need to understand the Cartesian sign conventions. If you understand the Cartesian sign convention very correctly, 80 to 90% of the chapter is complete. Okay. So, Cartesian sign conventions, distances measured in the same direction as the incident right are positive, those measured in the opposite direction are negative. All distances measured from the pole or optic center of the mirror lens on the principal axis, all distances measured from the pole, either the pole or optic center of the mirror, or for the lens case we use for the principal axis, on the principal axis. So, for pole for the mirror and optic center for the lens. Okay. The heights measured upward from above x axis and normal to the principal axis of the mirror lens are taken as positive, quite evident. Anything above is positive, anything below is negative from the principal axis. The heights measured downwards are taken as negative. Okay, fine. So, this thing has also been explained. Next is mirror equation. So, you should remember this 1 by v plus 1 by u is equal to 1 by f, where u and v are the object and image distances respectively, and f is the focal length of the mirror. You just need to be very thorough with the sign conventions, and everything will be very much easier. F is approximately half the radius of curvature. This derivation is also been explained in the subsequent lectures. F is negative for concave mirror, quite evident, and f is positive for convex mirror. These are nothing but sign conventions applicability only. Next is for a prism of the angle A of refractive index n2 placed in a medium of refractive index n1, n21 is equal to n2 by n1, which is equal to sine of A plus dm by 2 into sine of A by 2. You can change it to, as sine theta is approximately to theta, you can write it as A plus dm by 2 upon A plus dm upon A. Fine. Where dm is the angle of minimum deviation. So, these examples, this derivation have already been explained in the subsequent lectures of refraction through a prism. Okay. Next is for refraction through a spherical interface. So, this is your nothing but thin lens makers. This is nothing but the derivation for the spherical interface refraction. This is nothing but the lens formula, thin lens formula, and this is nothing but the lens makers equation. So, you just need to remember these. So, these are basically the 4 equations which you need to remember from this complete lecture series of ray optics. So, for refraction through a spherical interface from medium 1 to 2 of refractive index n1 and n2 respectively, n2 by v minus n1 by u is equal to n2 minus n1 by r. Thin lens formula is 1 by v minus 1 by u is equal to 1 by f. Lens makers formula is 1 by f is equal to n2 minus n1 or n2 1 minus 1 into 1 by r1 minus 1 by r2. So, basically if you go and add here, so n2 by n1 will give you n21 and minus n1 by n1 will give you 1. Okay. Then r1 and r2 are the radii of curvature of the lens surface. F is positive for a converging lens, f is negative for a diverging lens, and the power of a lens is, you just need to remember this. The definition is also been explained in the subsequent slides, subsequent lectures. So, power of a lens is nothing but the reciprocal of the focal length. Therefore, P is equal to 1 by f. The SI unit of power of a lens is diopters, that is 1d is equal to 1 meter inverse. Fine. So, this thing is also been explained. Next is, so basically the lenses which are being in contact with each other. So if several thin lenses of focal length f1, f2, f3 are in contact, the effective focal length of their combination is given by 1 by f is equal to 1 by f1 plus 1 by f2 plus 1 by f3 dot dot dot. And similarly, the total power of a combination of several lenses P is equal to P1 plus P2 plus P3 dot dot dot. What is dispersion? Dispersion is nothing but a splitting of light into its constituent colors. So basically, if a white light is being observed and it disperses, and as you can see different Vibgyor colors being observed. So it is splitting of light into its constituent colors. So this thing is also been explained. Next is magnifying power m of a simple microscope is given by m is equal to 1 plus d by f. What is d here? D is 25 centimeter is the least distance of distinction, and f is the focal length of convex lens. F is the focal length of convex lens. If the image is at infinity, we use m is equal to d by f, that is we just subtract 1 from that, that is m is equal to capital D by f. For a compound microscope, the magnification power is m is equal to me m naught. So here also we can find it as me m, m1, m2, m3 dot dot dot. A similar concept is being used here, and therefore the magnifying power is given by m is equal to me into m naught, where me is equal to 1 plus d by fe. What is the magnification due to the eyepiece, and m naught is the magnification produced by the objective. So eyepiece and objective, as the subscript is saying, E is eyepiece, O is objective. So approximately m is equal to L by f naught into d by fe. This also derivation has been explained in the subsequent lectures of your microscope. Okay. So where f naught and fe are the focal length of the objective and the eyepiece respectively, L is the distance between the focal point, which is tube length. L is nothing but a tube length. L is the distance between their focal points. Magnifying power m of a telescope is the ratio of the angle beta subtended at the eye by the image to the angle alpha subtended at the eye of the object, that is m is approximately equal to beta by alpha, which is equal to f naught by fe, where f naught and fe are the focal lengths of the objective and the eyepiece respectively. So this magnifying power of telescope is just explained in the part 1 of this lecture series only, this lecture 5 only, and right now after this I also explained to you that length of the tube or length is equal to f naught plus fe, length of the tube is equal to f naught plus fe. Fine. So hence that is the complete end of your complete ray optics and optical instruments. So course progress is also being done. So introduction has been explained, reflection of light by spherical mirrors has been explained, refraction and total internal reflection has been explained, reflection at spherical surfaces and by lenses has been explained, and finally refraction through a prism and optical instruments. So basically what were the two optical instruments which are needed? One was microscope and another was telescope. For basic class 12 subject, you just need to remember the magnifying power, the 3 types of magnifying power for a microscope, the magnifying power for the telescope, the what we can say, the length of the tubes for the microscope and the telescopes, and finally the 3 equations, maybe 4 equations. One was mirror equation, lens makers equation, and refraction through the surfaces. Okay. So that is the complete end of your course progress for the ray optics chapter also. So hence, thank you so much for listening. Thank you.